I guess we can start now. It's sort of like 11:01, and the whole the webinar and the introduce will be introduced by Dr. Pele Yakovic. We are like working here, working on the RADON Data Pipeline. Anyway, the stage is yours, Pele.
Yes, welcome everyone. Welcome to the third webinar of the RADON project. And today's goal is to learn how to design and deploy data pipelines using the technology called TOSCA and tools that we have created in the RADON project, which is a large European project that is now ending this month in June. And welcome everyone. So first, we'll go over the introductory topics. What are data pipelines? What is the RADON framework? We'll talk about OASIS TOSCA standard and talk about the TOSCA extensions that we have been working on in the RADON project. And after I have finished this kind of introductory as part of the webinar, then Chinmaya will show a demo how to use the RADON graphical tools to design and model data pipelines. So let's start with a short introduction of the RADON project. Like I mentioned, RADON is a large Horizon 2020 EU project. There are quite a few universities and companies involved all over Europe, starting from Estonia, where we in Tartu University are with Chinmaya, but there's also participants from UK, from Slovenia, from Italy, from Greece, and so on. The general goal of the RADON project is to offer a DevOps framework to EU companies and institutions, software industry, to enable them to adopt serverless function as a service model without this kind of typical vendor lock-in that you get when you use the public cloud providers. And we have around 40 people contributing to the project. Here you see some of the researchers involved. I am here and Chinmaya is here, but we have also, like I mentioned, people from many other universities and companies all over EU. The project itself started from microservices. The pattern were more complex applications that usually historically have been built as monoliths are no longer built as monoliths in nowadays, but they are rather built as individual services that can be designed and deployed as individual software artifacts, which can be then composed into more complex systems by making them work together, talking to each other. And in the this is the microservices here. And in the recent years, there has been an emergence of serverless functions, which can be considered very small microservices, often just a single function, whether it's written in Java or Python. I can write one such function and deploy it as an individual software service in cloud and have the cloud provider take care of everything else, how to execute it, how to schedule it, how to provide input to it, and what to do with the output of the function. So the cloud provider takes care of all the life cycle of such serverless functions. And once the function is executed, they measure how long the execution takes, often in milliseconds. The minimum billing time often is 100 milliseconds. And then I only pay for how long that the execution takes, for example, 120 milliseconds. And they can be individually scaled, they can be individually managed, and they are often executed in an event-based manner when there is a need to execute it, for example, a new record added to the database. And the goal of the RADON project was to design a DevOps framework for serverless applications using TOSCA, which is a standard for modeling cloud deployments. If you want to see more information about the serverless part of the project, then you are welcome to come to our YouTube channel, where you will see the previous webinars, and they will focus much more on the serverless side of the project. But let's talk a bit about the TOSCA standard, because it's the core of the RADON project, and it's important to understand the general aspects at least. So the TOSCA is a topology and orchestration specification for cloud applications. It's an OASIS standard for automating the deployment and management of cloud applications. It was started by a big consortium of companies and institutions, for example, IBM, and it is a cloud modeling language with goal to simplify describing what software should be deployed, how it should be deployed, and what are its relationships to other software and the underlying infrastructure. Its major goals are automation of deployment and management, portability, interoperability, and vendor-neutral ecosystem to provide you ability to avoid vendor lock-in. TOSCA provides a language for defining what are the software components to be deployed, what are their parameters, what are the lifecycle operations, such as how to install them, how to configure them, how to start them, and how to stop them. And it encapsulates everything that is needed to automatically manage these software components. So everything is described inside TOSCA. While the implementation details might be implemented using some scripts such as Ansible playbooks or Python scripts or shell scripts, but they are encapsulated into the TOSCA model as additional artifacts. And here is a very brief example of a TOSCA language. On the left side, it's the YAML format of the language, where it's written into a text file. And on the right side, here is a picture from the RADON project's graphical interface, which allows to manipulate and create the software artifacts. In this case, there are 5 serverless functions, Amazon Lambda functions in the middle. Here, there is this DynamoDB, where these functions are writing their output on, and there's also nodes to define where these functions should be deployed, and what are all the access configuration parameters needed to automatically deploy these functions. And one part of TOSCA is also to be able to define this infrastructure as a code, scripts or code, which defines what are the resources allocated to these cloud software components, whether it's the capacity of virtual machines that are to be deployed, or the limits of serverless functions. And the TOSCA model contains all the information how to deploy these, each of the individual blocks, how to configure them, and after building this kind of graphical model, which is called service template in TOSCA, you can use Orchestrator to automatically deploy it or manage it after reconfiguration. And like I mentioned, if you want to hear more about how TOSCA works and how serverless functions work, then you can check our previous webinars. Let's go into data pipelines, which is the main topic that we, together with Chinmaya, have been working on in the University of Tartu in part of this RADON project, and the main topic which this webinar and the later demo will be about. So data pipelines in general are some types of data processing functions, actions, services, or other software components that are composed into a sequence of actions or a pipeline. Inside the RADON project specifically, we needed services for automating the data migration, processing, and storage across multi-cloud environments to support serverless function as a service applications, where functions are deployed on different locations in the cloud or in the internet, for example, on premise or on multiple different cloud providers or different availability zones. and there was need to automate and manage the real-time data movement between these serverless functions. That we couldn't depend purely on the cloud provider specific serverless function integration methods. And the goal is to provide a set of reusable data pipeline component services as TOSCA node types that can be deployed as individual services and composed into more complex data management, these kind of services and pipelines, and they can be automatically managed using TOSCA graphical modeling tools and TOSCA orchestrators. So they can be deployed on demand and whenever needed, reconfigured and redeployed, or stopped if needed. So here is a very simple illustration of a data pipeline. In the middle, we have a serverless function deployed, which is a Lambda function deployed in Amazon. This takes input from S3. Actually, a change in S3, for example, a new object, new image stored in S3 triggers the execution of the Lambda function, and the Lambda function processes this image, for example, and writes the output to a different S3 functions inside Amazon. But let's say we have a need to first synchronize data from an MQTT data broker that is deployed on premise in our OpenStack, and we want data automatically that is published in MQTT to be automatically stored in this S3 bucket so that Amazon Lambda function can be triggered. And once the Lambda function has stopped its execution and written the output to another S3 bucket, then we want data to be automatically migrated now to a Google Cloud storage where we might have some other applications running. And this is what we want RADON data pipelines to enable, this kind of automated real-time migration of data between different clouds and different storage systems and cloud systems in general. And this kind of composition of different services, different storage services can be done automatically. And we create this kind of TOSCA node types to deploy, for example, listening to MQTT and storing it as S3 as individual software services that can be managed automatically using TOSCA. And in the demo part of the webinar, you will later see how to design these types of service templates and deploy them using RADON Orchestrator. So we wanted to support these types of data pipeline. However, TOSCA did not have a good means at the start of the project to describe the flow of data. So it was mainly designed for deploying cloud software components. So we extended the TOSCA models with data pipeline specific node types and models. And our goal was to provide a set of reusable node types that anyone could use as an open source and create more complex data pipelines by composing them either as a simple pipelines or as such directed acyclic graph to build more complex data pipelines. The underlying automation of data movement is implemented by Apache and i5, which is an open source project, or Amazon Data Pipeline Service for specifically building these services inside the Amazon cloud. And internally, to implement the actual installation of underlying software components, then Ansible is used to build this kind of playbooks for TOSCA node types to install, configure, start, stop, and unconfigure the underlying services and cloud resources, including setting up all the cloud infrastructure resources needed for deploying these software. So the RADON data pipeline models consists of mainly 3 types of data pipeline services. There's one more, but it didn't fit very nicely into this graph. They are mainly source pipeline blocks that are node types that consume data from some external service or storage. There is this midway pipeline blocks that transform data, send data to fast function to be processed and returned back. And the third type is destination pipeline block that publishes data to external services or storage, such as publishing to an MQTT broker. Each of these blocks is a separate software service that can be individually installed, started, and configured, and they can be composed at runtime into more complex pipelines. And there is also, like I mentioned, fourth type, which is a special type of standalone data pipeline that is not composed directly, but rather deployed as a individual data pipeline that can be still composed through different data sources. For example, one S3 bucket is output to first pipeline and input to the second pipeline. And when using RADON tools, you will see this more in detail in the demo part that will come soon. The user first accesses the RADON Web IDE, then opens the RADON Graphical modeling tool to design the data pipeline. Here on the right side, we have an illustration of what this data pipeline looks like in the graphical user interface. The user also defines where the pipelines are to be deployed. In this case, it's an EC2 instance in Amazon Cloud Platform. So also this infrastructure part is modeled by the user. Once the user has developed this data pipeline model, they will download the TOSCA service template and use the RADON Data Pipeline Orchestration plugin to validate that they didn't do any mistakes. Then they can deploy the service templates using RADON Orchestrator. And RADON Orchestrator is a straightforward orchestrator that does not usually need much other external information to deploy this model other than secrets such as the credentials from Amazon that you do not want to write directly into the models, but it doesn't need any other implementation details. And the RADON IDE looks like this. Chinmaya will show it more precisely, but it's a graphical web integrated development environment based on Eclipse J, where all the RADON tools are deployed as Docker containers next to the IDE workspace and deployed when user starts using the workspace inside the RADON environment. The graphical modeling tool is a web-based TOSCA editor that allows graphically to design new node types, to upload artifacts, and to design these kind of service templates and configure, defining all the needed parameters and define relationships. For example, what nodes are hosted on what other nodes. And the RADON Orchestrator is an orchestrator that can take the TOSCA models and deploy them, taking care of all the automation processes and activities that are needed. It can be used as a software as a service version where it has a graphical user interface where users can go and deploy the downloaded TOSCA service templates, or it can be used as a command line client to use a simple Linux command line command to deploy the downloaded TOSCA service template. And if you want some additional information, then you can go check our node types. They are available publicly. Anyone can reuse these TOSCA node types. And like I said, they are individual and deployable service templates. And you can use Xopera to deploy them to RADON Orchestrator. The data pipeline documentation is available in Read the Docs. So if you want to get more information how it works, all the RADON webinar videos and some previous videos will be published on our YouTube channel of the project. Most of the tools are available as open source on our GitHub, and our website includes all the other information such as some public deliverables. And now it's time for the demo part that will be given by Chinmaya. I will stop sharing my screen in a moment and Chinmaya can continue with the demo.
Thank you, Pele. Thank you very much. That was a nice introduction to RADON and the data pipeline and TOSCA and some other tools we'll be using in this demonstration. Okay, let me first share my screen. I guess. I hope you can share my screen. Okay. So in this demonstration, we have already seen that what is this RADON data pipeline, what is this RADON, and what's the capabilities, what are the different capabilities of RADON and RADON data pipeline. So in this demonstration, we'll see this service template. We'll see how to design the whole this cloud service So in this service, we will upload some of the data, some image data to a min.io database, and that data will be consumed by one data pipeline node, and that node will that image will be sent to one Lambda function, and that Lambda function will be responsible for grayscale that image, and then the output will be sent to the another Lambda function, and the second Lambda function will do blurring the grayscale image. So the output will be sent to one Google Cloud storage, and the same output will be also sent to one fast function, and that fast function will compress the blurred image file and will store in one blob storage. So this is what we have the Azure cloud, and here we have the Google Cloud. Here we have the AWS Amazon cloud, and here we have this OpenStack environment. So here you can see like how we are migrating the data from your OpenStack private cloud to Amazon cloud, then to Google Cloud, then to Azure cloud. So this is a very good example of migrating data across multiple cloud environments. And we'll see how it is easy to design the whole service and deploy this one. Okay, so for this one, what we need first is we need to go to the IDE. Okay, before you can log into the to this IDE, and you can register yourself, and you can log into this IDE. So this once you log into this IDE, you need to create a workspace. And just to save time, actually, I have already created one workspace. And once you enter to this IDE, you can see the list of tools what RADON is offering. So to design that service template, we need to use the RADON GMT. And if we open the GMT, here you can see GMT is the graphical modeling tool where you can design your service template, you can design or develop your node types. You can also play around with all the different relationships types and other elements. So here we have already, here we'll go to the service template. Here we can see the list of service templates already created. For this demonstration, we already created one service template, and okay, sorry, yeah, here we have the service template. Once we open the service template, we can go to the topology template, and here we can click on open editor to open the topology modular window. So in this topology modular window, we'll first see what are the different elements or different TOSCA node types are present. So here first, as we saw this, this was the service what we will be designing. And for this one, here you can see that OpenStack VM and AWS platform are there. So these are the like hosting environment. And accordingly, we have OpenStack data pipeline nodes. So once you enter this GMT, here you can see a list of TOSCA node types that are already developed by different units in this project. And to use the data pipeline related node types, you need to go to either data pipeline source or process or destination or standalone. So source is for consuming the data from a external storage unit, and it could be anything. It could be a Amazon S3 bucket. It could be a secure FTP server. It could be a Google storage bucket, and also like we have this process category where we have a list of on-turn data pipeline nodes to invoke the serverless functions, also to process the whole the image data or the data itself. And the destination category is simply just to publish your data, intermediate data, or maybe like the final resultant data you can publish. And standalone is something which combine everything, which combine both source, process, and destination. All the capabilities, all the functionalities are combined into each data pipeline nodes. So we'll be using the node types developed under these categories. So we have this OpenStack. We have also AWS platform. So above OpenStack, we have NiFi instance, and inside AWS cloud, We have platform and then EC2, then NiFi. So here EC2 instance is hosted on this platform and NiFi is hosted on EC2 instance. So NiFi software component needs one kind of one virtual machine to be installed, or maybe a Docker container. And at the top of this NiFi, we have consume min IO. So this TOSCA node will consume the data from a min IO endpoint. And we have already min IO database already created. And the IP of that min IO database is, we have provided that one as a property. And to access the data from that min IO database, we have already provided the credentials. And the credentials are provided through the artifacts. It is possible that you can provide the credentials directly to the virtual machine. That is also possible, but in this demonstration, we have used the artifacts way to provide the credentials. And also here we have provided what is the bucket name. From here we'll consume the data. And once the data are consumed, we'll send the data to image to one AWS Lambda function. And that Lambda function will grayscale that image. And then it will forward the output to another Lambda function to blur that image. And then here the output will be, here the output will be forwarded to two different data pipeline nodes. One data pipeline node to invoke an image fast function that will compress the image and then store in Azure Blob Storage. And the other node is will be storing that blurred image to Google Cloud Storage. So once you have designed everything with all the required properties and with all the required artifacts, you can save the service template. Yeah. Once you have everything configured with properties, artifacts, requirement, capabilities, and once everything is done, you can save the service template. And once it is saved, you can simply close this window, and then you can go to the service template in the graphical modeling tool. Here you can export the service template in a SASA format. You can either export to the IDE and IDE, then it will appear over here. Or what you can do, you can simply download this SASA file. So in this demonstration, what we'll do, we'll simply download this file. And once it is downloaded, once it is downloaded, we'll upload this file. We'll bring this file to the virtual machine where I have already installed the X-Opera orchestrator. So the SASA file will be passed to the X-Opera CLI to deploy all the required node types, whatever we have provided in that service template. Okay, so I have already downloaded this one, and once it is like downloaded, you can simply what is this? Yeah, you can simply like rename this file to unzip, and then you can simply unzip this one. Once it is unzipped, what you can do inside, you can see all the related definitions are present. What we'll do, I have already created a virtual machine, and where I have already installed the X-Opera orchestrator. So in this, okay, so what I'll do now, I have already uploaded all the files to this virtual machine. And in this virtual machine, you can see that we have all the related node types, so node definitions. For example, this is the main service template TOSCA file. And in this TOSCA file, if you see, and this is the service template we have already created. Here's the NiFi instances, and we have the Invoke Lambda functions. All the informations are already in this TOSCA file. So we'll get back to the deployment. Once we have everything ready, what we can do here, we'll simply deploy this one. Okay. Here I need to issue this Opera command that will deploy on this TOSCA file, the service template. So here Opera deploy, clean means everything will be start from the very beginning. And here is the path to that service template. So, okay, I'll simply, that's good. Okay, now it started deploying one after another. Here you can see that now it started deploying AWS platform. So if you, sorry. Okay, here it is deploying the AWS platform. So in this AWS platform, it will simply just configure and install and configure the related packages. For example, AWS CLI, it will install, and some other related packages it will install. Once this AWS platform is installed, after that it will create one OpenStack virtual machine. So we already have the OpenStack cloud in the university. So we are using that, our private cloud. So right now it is deploying this EC2 instance. Sorry, it is already created this OpenStack instance. That OpenStack virtual machine is already created before, so that's why like it didn't take much time to create the new virtual machine. But in this EC2, here it is now creating one EC2 instance, and it will take a little bit of time because once it is EC2 is created, then it will install the software component. For example, NiFi. In the meantime, what we can do, we can see some of the other data pipeline nodes. Okay. Okay. In the meantime, like if you have any questions, you can ask, because this one will take a little bit of around 10 minutes, somewhere around there. And we can discuss here like some of the other node types we are offering. So in the source, what you can do, from where you can consume the data, you can consume data from Azure Blob Storage. You can consume data from Google Cloud Storage, from MQTT, from MinIO, what we are using over here. Then you can consume data from S3 bucket. Then you can consume data from FTP server as well. And at the same time, you can also publish data to all these storage units. Now, to process the data, you can, what are the different node types we have? You can encrypt the data using encrypt and decrypt nodes. You can invoke a fast function. You can invoke a fast function with the image data as the input. You can invoke the Lambda function. You can invoke a OpenFast function. And also like you can invoke a Python script or something in the command prompt using this local action. So these are the different node types we have. And in the standalone, you can copy the data from DynamoDB to S3 or from S3 to DynamoDB. And these are like very simple way to deploy these services. For example, if for DynamoDB to S3, you just need to provide the database name and some credential information, and the S3 bucket name and S3 bucket name and the credential to S3 bucket. So before that, the EC2 instance is already created. Now it will try to log into that EC2 instance and install the NiFi at the top of that EC2 instance. So, okay, coming back to this node type, NiFi, here if you see in the NiFi, we have the properties called port number and the web interface, whether you want to make it public or not, and the component version. So that means this software component, once it is installed, we can access this NiFi instance, NiFi software component using the IP of the EC2 instance or the OpenStack VM, wherever it is installed, IP of that instance and the port number we have provided over here. But to access that one, we need to make it public. So these are the other two main properties we need to configure this NiFi instance. Okay, now what we'll see now, we'll see this MinIO database. We have already created this MinIO database where we have first bucket, and this is the bucket name. We have one image data, one.jpg. Let's remove this one and let's keep the bucket empty. So in the whole service template, what will happen once we upload any image data to this Minao database? It will automatically processed using the Lambda functions, what we have already created before. So we'll use this image blurred NiFi, this Lambda function, as well as we'll use this Lambda function. So we'll use these two Lambda functions to process, to grayscale and blur the image. And then the output will be moved to a Google Cloud storage bucket. So here we have the container name or the storage bucket name, you can say. So right now it is empty. And then the same blurred image will also be passed to this compress fast function. So this is also we have already developed before and already been deployed over here. So the blurred image will be passed to this compress, and this function will compress the image data, and then it will store to the Azure blob storage. And the blob storage, here we have the blob storage where we do not have any data so far. Okay, so what we are doing here, NiFi is already installed, configured, and started. Now it is deploying the PubGCS. So PubGCS is publishing the data to Google Cloud Storage. Now, which part it is? It is about this part. So PubGCS, what it will do? Okay, let me go to the service template. Okay, here is the service template. So here you can see the publish PubGCS. So it will deploy this pipeline at the top of this NiFi instance. So if you see here, okay. Can I move? I'm not able to move that. Okay. So if you see here, this one is hosted on this NiFi instance. And so this one will be first created, and then it will be configured, and it will be created on this NiFi instance. Okay, now it is created, and now it will be configured. And once this one is created, after that, maybe the invoke image fast function or the image this Lambda function node will be deployed. Okay, so let's use this time now. What is there in the PubGCS? So if you see this this PubGCS, what are the different properties we have provided? We have provided the bucket name, which is RADON GCS. We have provided the project ID and the credential file. So if you see the artifact of this one, yeah, in the artifacts we have provided the credential file. So you can see like in the properties to access. Sorry, it is getting slow. Yeah, in the properties we have provided get artifact, self, and credential file. So this is something you need to mention, that you need to tell this this service template that get the credential file from the artifact. So these are the three main properties. So we have we need to provide, and apart from that, the common properties we have for all the node types are scheduling strategy and scheduling period cron. So these two are needed to schedule your data movement. So if you want to schedule it for like once in a day or once in every hour, you can schedule according to you can schedule accordingly, and you need to provide the corresponding cron syntax over here. Now, if we see here, this is already deployed, configured, and already started. Now it is deploying the image fast function, and then okay, it is already created, configured, and started. Now it is deploying the invoke Lambda function. Okay, so this one is already deployed, and then this one is also deployed. And then okay, now it is deploying this image blur function. Okay, now it is deploying this one. So you can ask like why it is why this public GCS first this one got deployed, why not this one? Here, if you see the relationship between image blur, this node type, and pub GCS, here we have connection. The requirement of this this node type, this TOSCA node, is this pub GCS node. So that means before it start, it needs this pub GCS to be deployed and already in the start stage. So that's the reason why it is why the orchestrator is first deploying the this pub GCS TOSCA node. And okay, so here you can see that this Lambda function is already created. It is configured, and after configuration, it is also connected with the Invoke Lambda. This is connected to Invoke image first. That means this one is connected to this image first function, and then this one also connected to pub GCS. So image, this one also connected to this node type, this TOSCA node. And then it is now deploying, okay, this one is finished. Now it is deploying the Invoke Lambda, the other Lambda function. Sorry, other Lambda node. So now it is deploying this one. Once it is deployed, then it will configure in the sense that it will create the relationship between this node and this image blurred node. Okay, if we see the Invoke Lambda node, here the properties are very, very few properties we need to provide. One is the credential file, and one is the function name. And this function name, it is assumed that this function name is already there. And then the region, and that's all. So you just need to provide these three information, and it's enough for the X operator to deploy. So it is already deploying the Invoke Lambda. Okay. And then once it is done, now it is deploying the NiFi. That means it seems like all these node types, everything are already deployed. Now it is deploying this NiFi, which is at the top of OpenStack. And at the top of NiFi, we'll have the const min IO. Okay, NiFi is deploying. Okay. So we have already seen what are the different properties of NiFi. Okay, now it is deploying const min IO. Okay, it seems there seems some issue with const min IO. Okay. Let's resume this one. Okay, so there was a mistake with this const min IO. I guess seems to that there should be some bug for which it was unable to deploy. Now it is deploying the const min IO. So here you see that we have provided this resume flag, so that it will it will start from where it stopped. So it will resume the whole deployment process. Now it is deploying this one. Okay, and now it is configuring the const min IO. So here you can see that const min IO is now connected to this Invoke Lambda. So that means this relationship is now already established. Okay. Okay, now it is starting the consuming IO. Okay, that's good. Everything is already like deployed. Now we should be able to see if we upload anything to here, we should be able to see the resultant files in the Google Cloud Storage. Let's upload something to this one. Let us say, okay. Let's upload this image file to min.io. Okay, now we see that this image we have uploaded. Now let us see if Google Cloud Storage we should see the blurred image over here. If not, then there should be some issue with the NiFi or maybe the pipeline nodes. It seems everything is okay. It seems like something's not running. Okay, let's see the NiFi instance itself. We have the EC2 instance, and the IP of that EC2 instance was this one, 3.1.2.0.5.1.0.2, and let's put that one. So here I have accessed the EC2 instance and the NiFi with the port. And if we log into this one, we can see if there is any issue with this NiFi instance. Just to make sure that all the pipeline nodes are working. We can see that something is stopped over here. We just need to start. Yeah, here it is. So let's start this one. Sometimes it behave strange. Okay, now that one is started. Now let us see if we see the result. Yeah, we see the result. The result is, it should be blurred. Yeah, it is blurred. Let's compare with the original one. So here we have the original image, and here we have the blurred image. So any image we upload to this min.io, you should see the resultant image in the Google storage very quickly. So, okay, we have uploaded another new image. Image was logo 3. It seems it is taking a little bit of time. Let us see the Azure storage. Okay. Here we can see the uploaded image. Both the images are already compressed and stored over here. And here we can see the blurred image. Now we should see. Yeah, here we can see the blurred image. So you see like how it is easy to design this whole service where you need to move your data from your private cloud and to AWS platform, to Google Cloud Storage, to Azure Storage. It's very easy to combine all the different nodes and move your data freely. And this addresses actually one of the bigger issue that data vendor locking. And you don't have to worry about which cloud you need to provide. And here, like you can, it's very reusable components. For example, like if you don't want this OpenStack VM, then you can simply bring this NiFi instance to the NiFi software component to EC2, or you can simply replace this EC2 instance with something else. So this conclude the whole demonstration process. You see how it is a bit easy to design, deploy, and reuse the components. And that's all about this demonstration. And if you have any questions on this one, You are welcome.
Someone has raised hand.
Okay, Pujaras is asking something.
Yes.
Yeah.
Yes, in the binary, in the node types, if we required our own custom node types, then is there any we have to design our own node types, like custom node types if it required? Say, for example, you have an OpenFast function node type to invoke OpenFast function like that. If I want for fission, then I need to design a node type for the fission.
That's a good question. So yes, definitely you can. If you find that some node types are not there, and if you want to customize something, then either you can simply add a new node type, and that will also automatically reflect over here in this over here. But if you want to customize some existing one, you can do that once. For example, if you want to customize the OpenFast Invoke OpenFast node, then you can simply go there and you can customize. You have all the facilities, like you can put your own properties, you can put your own attribute, capabilities, your requirement, everything you can define over here. You can also define your artifacts, you can define the inheritance. So yes, it is possible that you develop your own node types. You can develop your relation types as well. Thanks for this question.
Adding to this question, like suppose
Okay.
if I want an OpenFast function node type, when I drag and while deploying to the TOSCA, does the OpenFast infra should be existing, or TOSCA will handle to set up the OpenFast infra?
Okay. Let us say if you want to use the process very specific to this node type, this node type assume that you already have the OpenFast infrastructure. So we'll simply invoke the function which is available in this OpenFast infrastructure. This will not deploy the function. To deploy the function, you need to have different node types. For example, this Lambda node type. And this assumes that the function is already designed, developed, and it's already available in the AWS platform. So this node will not deploy the function, rather it will simply invoke that function. It will simply reuse the function. So the whole data pipeline is mainly focusing on movement of data. And for that, we have provided some of the hosting environments. For example, like you can set up your own AWS platform. You can set up your own Azure platform. You can set up your own Google platform. So definitely, we will continue this one probably in future with some other project, and you may have probably you'll have some more node types in future.
Yeah, thank you, and a very good presentation. Yeah, thank you.
Thank you. Okay. Is there any other question? Okay. Seems no other question. But still, if you want to know more about this one, then probably you can go to the RADON website. Yeah, RADON S2020.eu website, and from here you can see all the related informations. Apart from this, there is we have the GitHub repo for RADON, and in that GitHub repository, sorry, something. Okay, in the GitHub repository, you can see all the related tools. Everything is open source, so if you want to use your customize anything, you can go ahead with your own customization based on your requirements. And that's all about RADON Webinar 3 on the data pipeline, which is focusing on movement of data across multiple clouds. And that's all for this webinar. Is there anything left? Seems no. Okay. So thanks for attending this webinar, and hope we'll see soon with maybe some other technology or some project. That's all. Thank you.
Thank you, Chinmay.
Thank you.
Thank you.